Okay, and this second example for this last part 3 of section 6.4, the last section for this unit, we're going to look at the cation ammonium, NH4, and look at its Lewis structure and why it's got this extra plus charge. Again, we said before, we're going to add up the total number of valence electrons for the compound, NH4. We'll determine the central atom. Well, I've got nitrogen, and hydrogen can never be the central atom, so by default, it's nitrogen. Plus, there's only one of them. And we're going to bond the other atoms to the central atom and update our count. So for our total valence electrons, we have nitrogen, hydrogen, there's 4 of them. We're going to bond that one, bond the second one, bond the third. This one has 4, NH4. Our total valence electrons, nitrogen, had 5, it's in group 15, and there are 4 hydrogens, so 5 plus 4 is 9. So we have a total of 9 valence electrons to start with. We just bonded the 4 hydrogens to the central atom, each bond taking up 2 of the valence electrons. So we've used 8 in the bonding process. And remember, nitrogen is in group 15, so it has up, down, left, right, up. So it has a lone pair. One of the atoms of the lone pair unspin paired and bound up with the 4th hydrogen, leaving that 5th electron all by itself on the nitrogen with no more hydrogens to bond to it. So we've used 8 in the bonding, and we have 1 left over. Now typically we take the extra electron or electrons and put them on the outliers to reach stability, but since they're all hydrogens, hydrogen only needs 2. So they're already stable. All 4 of them are already stable. So I still have this 5th extra unpaired valence electron on nitrogen that can't be delocalized like we did in phosphate. There's nothing to go out to. All the hydrogens are stable. So I can't transfer it to the outliers. In this case, it simply leaves, making the overall group, because it's delocalized, it doesn't belong to anybody, it leaves the group. And so, since I've lost an electron, I now have a positive or a plus 1. So that electron just gone. And we study Lewis acids. It'll explain why if you ever take chemistry 2. Right now, as we know, is that the overall group itself is now a plus 1. That 5th one couldn't bond to anything else, and it's no longer needed because the nitrogen is stable. It also 2, 4, 6, 8. It's happy, unlike the phosphorus, which is also group 15 in the phosphate. And that is why that is the only one that is a cation polyatomic. So VSEPR, the shape of the molecule determines many of its physical and chemical properties. The VSEPR model stands for valence shell electron pair repulsion. And that helps us determine the shape of the molecules. As you saw with the other lesson on the 3D shapes of the S-node tree, this is what gives us the idea how it's going to be if I can blow it up and see it as a 3-dimensional. Places are shared and unshared electron pairs as far apart as possible on the central atom to minimize this repulsion. If you were in class, you would have a periodic table that's a class set, and on the back we have the molecular shapes. This is like your yes-no tree. You look at the things, they call them electron domains, look at the things on the central atom. If I have 2 things on the central atom, I have no lone pairs, but I have bonds or shared pairs. In other words, I'm sticking atoms on there. It's linear. If I have 3 things stuck to it, it's 3 atoms, no lone pairs. It's trigonal planar, the triangle, where they all lay in the same plane. as you see here. If I have four things, they're all atoms with no lone pairs. It's a tetrahedral, where we had our central atom here, and these guys, there's 4 points on this big pyramid with this in the center of it, far apart as possible. If I have four things, 3 of them atoms, 1 of them a lone pair, the ghost. Instead of being trigonoplanar, there's a ghost above here. They feel it, even though you can't see it, and they try to get away from the ghost. So it creates a triangular shaped pyramid, trigonal pyramid. If you have 4 things, 2 of which are atoms, and 2 that are lone pairs, these 2, instead of being linear, like up here, we've got 2 ghosts. These 2 atoms feel it, they try to get away, so they pinch down each other as much as possible before they start pushing each other away, and we have bent. So that is exactly what you saw on the yes-no tree they have. So either one of them are available. If you want to screenshot this and have this, because this makes more sense to you, then by all means, please do so. And that is the end of this section, the end of the unit, and the end of the second problem.